So this is a second question from your sample midterm exam. Let's take some time to understand the problem description itself. So we are dealing with two products. One is Inspiron, one is Latitude. So I'm just going to paste it here as I talk through. And for the coming month, Dell Tech wants to decide how many of each model to assemble and test. Each laptop will go through two separate processes. So we got two separate processes. I believe one is assembly, the other one is testing, right? Before it is released to the market. The expected demand during the planning period is provided and doesn't want to assemble more than the demand, does not want to assemble more than the demand. So this becomes important cue as you solve this linear programming problem. Following information will help you determine the contribution from each unit, right? Contribution from each unit need to be determined. The retail price is here, and cost of component parts are also here. The number of hours required for each model in each process is provided in table 1. The cost of each hour is provided in table number 2. So table number 1 has half information about the contribution, and table number 2 has the other half. You will be needed to calculate the contribution. The total available assembly and testing hour is provided. So it sort of reminds you that there is a hour capacity, hour cap, hour maximum upper bound you need to consider. Cannot be increased, right? So cannot be increased. So it looks like we have an upper bound we need to consider as we try to solve it. So I already copied table number 1 to here, and I'm going to copy table number 2 here as well. So help Dell to identify the assembly quantities for each model that maximizes the total contribution. So assume that those demand information is already passed down from the marketing department, so operation department no longer needs to worry about what's the demand, right? So let's solve this using a linear programming approach. So there are 3 pieces of information you need to obtain before you jump into the solver. That's always faster to solve as you spend some time to think about this question itself. So the first piece of information is, do we know the parameters? What are the decision variables? Okay, so we have some parameters here. We have some parameters in terms of demand cap and retail price and raw material, and I believe the problem has provided enough so that we can determine what is the contribution. Right? What are the decision variables? What are the decision variables? So since this is allocation problem, obviously, the decision variables that what we're looking for as a decision variables is the quantity of each model. So that's about all we need. So quantity for Inspiron and Latitude is actually the decision variables that we'd like to find out. And parameters are just here all over the place, but we're missing one of the key parameters that we need to calculate the total contribution. So why I'm doing total contribution? Because it's reminding us to maximize the total contribution. Right? So we need to figure out what is the total contribution based on a quantity we'll be determining later using the solver. So we do not yet know what is the contribution for each model. Okay, this information is actually hidden. It's not directly provided, but need to figure out in using some step. So we have all these components are one of the big part in variable cost. We need labor cost, which is another half of the variable cost. Okay, so although it is not provided immediately, we can actually calculate that using the information provided. So I'm going to copy cost in each hour here. So each hour of assembly is $11. Each hour of testing is $15. Okay, so using that, we can sort of calculate the total labor cost for each model. So the labor cost will be some product of this and this. Okay, and that will give us the total labor cost for Inspiron. Hope this step makes sense to you. And I'm going to absolute reference D5 to D6 because we're going to use that again to calculate latitude total labor cost. So some product. So this is equivalent to 6 multiply 11 plus 2 multiply 15. Okay, so with the total labor cost, total components part cost for each of those models, I think we have all the information we need to figure out the total contribution, right? So the contribution is P minus V. P is retail price minus your component minus labor. Hope that makes sense. We do that again for your latitude model. Okay, so our total contribution wise, it's going to be the labor cost multiply, it's going to be contribution for Inspiron multiplied by the quantity of the Inspiron plus contribution for latitude multiplied by the quantity of latitude. So aka sum product. Contribution parameters with a quantity which is to be determined using your solver. So this is your decision variable. So to be determined by the solver. All right? And the second piece of information we need to think about is, of course, objective function, which is already defined here. Okay? This is the objective function. We're trying to maximize it. Maximization problem. And lastly, we need to figure out what is the constraints. So we have some constraints spreaded here and there in the problem description. But let's take a look at the first very obvious constraints from the first description. It doesn't want to assemble more than the demand. So there is a limit in terms of how far you can go, right? So you don't want to make more than 600 for Inspiron. You don't want to make more than 1200 for the latitude. So that's the demand side of constraints. So if you think about what's the other piece of constraints here, which is the total available number of hours for assembly and testing. Okay, so total number of hours assembly for both Inspiron and latitude combined should not increase 10,000 hours. Okay, that's the same with the testing, which should not exceed $3,000. So we got, let me just make it a little bit more clear in Excel. I'm going to say it as a decision variables. I'm going to make it as objective function. And the last step is going to be constraints. Okay, so we got here fixed. This one should be calculated, right? It should be calculated. So meaning the contents will be changed as we type different numbers here. Okay, so if you're wondering why I'm typing a random number here, just arbitrary number here, because don't worry, because solver is going to eventually replace the optimal solution with those numbers. The reason why I'm randomly typing something now is trying to see whether this function is changing as I change numbers. Okay, so apparently it's been set up correctly. That's why you're seeing that as I change numbers, this number also changes. Let's put down all the constraints. Maybe these information is better. Go somewhere else. Okay, since we already know where we're going to use it. So I'm going to put down demand constraint for inspiron. Okay, and then you have a demand constraint for latitude. And then you have hour constraint for assembly, hour constraint for testing. Okay, so here obviously demand constraint is 600, right? So I'm going to put down total of each, right? And then relationship. And also put down maximum or minimum. Okay, so with that, we know that our maximum demand is 600 for inspiron. Our maximum number of latitude should be 1200. So the total number of inspiron will be total quantity determined by the solver. Total quantity determined by the latitude. So the relationship wise is less than equal to, okay? Less than equal to. And hours constraint for assembly. So this is total number of hours that's dedicated to both models. So for each number of inspiron, you need to spend 5 hours, and you are making this number of inspiron. Okay, and you also need to add it. It's not the end. Okay, we need to keep adding it. So this many number multiplied by this hour for each unit. So that will basically gives you a calculated result for all the hours went into the assembly. Okay, so it's the same with a testing hour. I'm going to do that a little differently with a sum product. Testing quantity. Okay, so that is equivalent to 1 hour multiply number of quantity of inspiron plus 2 hour multiplied by the number of latitude. Okay, and then sum them up. That's what it is. So I can actually replace this with a sum product. This. So we're spending way more hours in assembling when compared to the testing. Okay, what's the total maximum number of assembling? 10,000 hours. What's the maximum total number of testing? 3,000 hours. So we all have less than equal to relationship. Okay, we also know that this is a sort of calculated field. Okay, so I think we have all the elements that are needed to run the solver. The next part is actually the most challenging part, identifying the solutions, but luckily we don't do that manually. So I'm going to run my solver, and I am going to specify the objective function, which is 7880. This is a maximization problem. We're trying to maximize the contribution by changing quantity of latitude, quantity of inspiron. Okay, and then we're going to add constraints. So all the constraints have the same directions. So conveniently, in this case, you can just highlight all the calculated total and highlight all the upper bound, and this will remain the same. And I'm going to also add a second constraint here that basically says they are all integer. Okay, all integer, and then we click OK. So integer constraint cells must include only variable cells. Okay, that's good. I think I know what's wrong here. Your quantity should be integer, right? If you think about the quantity we're trying to determine, that should be the integer. So because all the hours are also integer, this is also likely to be integer, but this is actually calculated cells. So it makes sense that we exclude it from the specification. And click OK. And go with simplex LP. Click solve. Okay. So I think I got a little different results in the morning class because I forgot to specify the demand upper bound, right? And then I got the same result in my second class in the morning, which has the same solution. So 560 and 1200 is actually the unit that you want. Okay, that can help you maximize the contribution. So it seems like it involves a lot of different steps. The really key is to straighten up your logic. Okay, to identify the key parameters, and most importantly, your decision variables. Right, your decision variables here, and then you need to identify your objective function, which is to be minimized or maximized. Okay, they got to be clear, and then you should be able to formulate your constraint in a form that you can help Excel recognize the relationship between the calculated value and the upper or lower bound. In this case, it's all upper bound, so it's quite convenient. Okay, so remember, if you take a look at the D12, the example we worked in Monday, Wednesday class, it's actually very, very similar to this problem. In fact, you just need a very little tweak to almost get it work for purpose of this particular problem, right? Instead of XPods, you can supply Inspiron. Instead of latitude, you can supply the instead of blueberries, you can supply latitude. So you can change up some of the things here, and your green color cells are your decision variables. That make sure you do that. That's actually easier for you to recognize in the later phase of the calculation. And I think we have more than two constraints in this particular problem, because not only we have maximum hour limits, we also do have demand cap. We don't want to go more than certain demand, certain number of demands. So yeah, so as you can see, different problem, but with almost identical structures. Okay, so at least help yourself get familiar with this workflow from getting from problem description to identify those informations. Okay, so they'll really help you straighten up the rest of the steps. Okay, once all these are identified, with a solver, it's basically to fill in the blanks here using the information you have prepared on your spreadsheet, and then to run it with simplex LP. Okay, this concludes the demonstration. I hope this helped.